Hey everyone, welcome to the AIPG Lunch and Earn seminar for March. I'm Aaron Johnson, Executive Director of AIPG, and I really want to welcome all of you and thank you for coming. If you need a CEU certificate for your reporting for your professional geologist registration, if you would, please put your name in the chat and we'll make sure that we get a CEU certificate sent out to you. Also, a couple of quick things. The annual meeting registration is open. This is our 60th anniversary annual meeting in Covington, Kentucky. We'd really like to see you guys come out and support the annual meeting. The officer ballot is out. So if you're an AIPG member, it's time to vote for the officer slate for our leadership in 2024. And finally, we've got a little information out about an AIPG trip that will basically be a geological trip to Scotland. It'll also support the AIPG Foundation. So if you're interested in any of those things, take a look at your email and you'll see those come in. Today's Lunch and Earn seminar was going to be presented by Doug Bartlett. Doug is a founder of Clear Creek Associates. He has a long, storied career in geology with more than 30 years of experience in mining and mine permitting. And he's a past president of AIPG. Doug, thank you for putting on a webinar for us today. The floor is yours.
Thank you, Aaron. I appreciate it. And thanks everybody for joining me today. Let me get my screen going here myself. So this topic, groundwater issues encountered in mining, is a huge one. There are many, many issues. So it is something that I'm not going to be able to cover comprehensively in an hour. So what I thought I would do is break it down into some general stuff, but also talk about some things that I have found very interesting in my career over a long period of time, and that I think you'll find interesting as well. So I'm going to talk about I'm going to break this down into different phases of a mine's life. So planning, operations, and closure. And we'll talk about the hydrogeology aspects of each one of those, and then I'll have some conclusions at the end. So my background is that I have a bachelor's and master's from Colorado State. I have actually 46 years of experience as a consulting geologist. I spent a brief time working as an exploration geologist for Anaconda Minerals, but most of my career has been working as a consultant, first for Dames and Moore for about 22 years in both Denver and Phoenix. Here in Arizona, I was the geoscience manager. And then in 1999, we started Clear Creek Associates, which we're now part of another company called Geologic Associates. My expertise is actually in groundwater modeling, hydrogeologic investigations at mining properties, the design and testing of bedrock monitoring and production wells, and a whole lot of other stuff. I am a qualified person for the Canadian National Instruments 43101 reports for different properties. I do expert testimony work, not necessarily my favorite, but it is part of what I do. And I spent a lot of time with AIPG. I was on the executive committee for about 5 years as both treasurer and president. And I'm a registered geologist in 5 states, certified hydrogeologist in California, as well as CPG with AIPG. So first of all, my experience is in hard rock mining in the Southwest US. So I don't really have a lot of experience in other parts of the US or in foreign countries, although I have done some work. But that most of my experience is in the Southwest US. So this talk is going to have that flavor to it. And a lot of what I do is confidential, so I've had to genericize a lot of what I'm going to talk about. That's just the nature of the beast in consulting. And I'm not going to talk about sand and gravel, coal, uranium operations. So water is an absolutely key part of mining. There's either too much of it or too little of it. And it's just rare that you actually have the exact right amount of water. So that's what we deal with hydrogeology and mining sites. And it doesn't really matter how rich an ore body is. If you don't have water, it's not worth anything. So water supply is absolutely critical. I think the best way to look at this is to break it down into the life cycle of a mine. So mines can last a really short period of time, like 5 years or less, or they can be greater than 100 years. So the three main chapters of a mine's life are the planning, the operations, and the closure. So let's first talk about planning. The hydrogeologic setting is common to mining operations. So we're always, for any mine, we have to understand the hydrogeologic setting. There's opportunities during the mineral exploration and development phase to obtain really good information that is essentially free. So it's important to be at the beginning of a project, and I'm more and more seeing that as we get contacted by potential mine developers who are in a greensfields kind of setting where they haven't started doing anything yet, and they want to know what can they do to help with the eventual definition of the hydrogeologic setting. So we use a lot of different tools for assembling data. We use ArcGIS, Leapfrog, various databases. We collect surface geophysics and downhole geophysics. There's exploration and test wells that are constructed in the fractured rock aquifers. We have to have ongoing monitoring for both water levels, meteorology, water quality. And a lot of the mines require a lot of different sub-disciplines to develop. So the cross-pollination of these disciplines is super important and something you got to kind of work towards, because a lot of us work in little silos and we don't know what's going on around us. That's not a good thing. And we can provide good benefit to the mine if we understand how we can use other disciplines as part of what we're doing. Groundwater models are essential. They're an essential tool for all hydrogeology. And I'll talk about that a little bit. And then permitting is the other key reason why we do hydrogeologic studies. And I list here several. UIC is underground injection control. Arizona has the Aquifer Protection Permit Program, but most states have something similar or some other state-specific permits. And then exploration, mine plan of operations is another one. And there's many others. So most of the mines, certainly the mines that I work in, are in hard rock settings. And that includes fractured igneous, sedimentary, metamorphic terrains. Groundwater flow is strongly influenced by fractures, joints, and anisotropic responses to pumping is very common because of that. We're also usually adjacent to basin fill valleys that are filled with basin fill material, and these can have significant permeabilities and store a lot of water. This is true in the Basin and Range province in the Western US, pretty much everywhere. So these two types of aquifer settings, hard rock and basin fill, are often strongly linked. Now, the field investigations can be quite complex because it requires a lot of drilling and testing of wells. And this isn't always financially feasible for smaller mines. So we have to live with what little bit of information we have. That's a key part of what I do. So here's a fractured rock setting. This is in a bottom of a pit, obviously, and you're looking up on the sidewall here, and you can see a crack. This is a fault, a major fault, and it's offsetting different rocks, rocks of different types on either side. And so the question is it a barrier or a conduit to groundwater flow? And often they're both, but in this particular case, this mine, it's a barrier to flow. And so the water level is quite different on one side versus the other side. So here's a cross section of kind of a typical setting we have. The mine itself, the open pit, may be up in the mountainous part, what I'm showing here is a fault zone that produces water, and we have pumping wells that are producing water out of this fault zone. Then we also have an adjacent basin with basin fill material. Usually, this is very common. We have usually 3 layers in these basins: a lower conglomerate or coarse-grained aquifer basin fill material, a middle clay unit or clayey silty unit, and then an upper very shallow coarse-grained alluvial setting. And what I'm showing here is the water table. That blue line extends above the land surface as you get out into the middle of the valley, and that's because the water in the basin fill aquifer at the at the base of the clay unit is under pressure, and you can get artesian flow in that kind of a situation. So there's, again, lots of opportunities for collecting information during the exploration and development drilling program. What we like to do is, I'm going to see if I can put my pointer on here. What we like to do is try to identify the locations of significant faults and fractures that are encountered in holes, identify lost circulation zones, use RQD, which is rock quality designation, or fracture intensity, to help us understand how the rock may be permeable or not. Get downhole geophysics, especially electric logs, sonic logs, or acoustic televiewer logs are all very helpful. And then characteristics of basin fill overlying the bedrock is often completely overlooked by exploration because they don't really care about it because there's no ore there. So a lot of logs I've found don't even start until you get into the bedrock. Well, that's unfortunate because we need to know that for the hydrogeology. So that's one of the things that you sit down with a mine owner and say, look, when these guys are drilling through alluvium, take a log, make sure you're collecting information about what's in the basin fill. And then finally, surface geophysics, induced polarization, gravity, or AMT methods are very helpful. So here's some examples of what I'm talking about. This is core, obviously a nice mineralized piece of core. And from this, we can gather the rock quality designation and fracture intensity. I'll talk about that a little bit more on the next slide, couple slides. Over here, we have the acoustic televiewer log. This is a log that allows you to get oriented, essentially like oriented core, where we can figure out the orientation of fractures that are encountered. That's what you see here. This is a folded out version of this. This looks like core. That's what it looks like. And then we also do surface geophysics. This is controlled source audio magnetotelluric data here that allows us to make interpretations down to 2,000 to 3,000 feet depth and helps us decide where we're going to drill. So logging core is very important. We do a lot of it, and rock quality designation just is a way to measure that and gives it a number. So what you do is you take the total length of the core that's greater than 10 centimeters in length and divide that by the total length of the core run. So a high quality RQD would be more than 75%. In other words, more than 75% of the core is greater than 10 centimeters in length, and low quality would be less than 50%. Now, from a hydrogeology standpoint, I like the low quality better because there's more fractures. Another way to look at this, and the problem with the RQD is that the resolution is only to the length of the core run. So you can't really zoom in on small zones that have very high fracturing, which may be important. Fracture intensity, on the other hand, is more of a subjective approach. So you can isolate small zones less than a foot and define their fracturing characteristics. So this is how fracture intensity works. It's subjective. So you look at this box of core. This is a fracture intensity of 1. There's hardly any fractures in it. 2 is a little bit more, 3 more, and finally, by the time you get to 5, it's basically rubble. So it's qualitative, but it does very much help in figuring out the permeabilities. And then sometimes we'll take this information, combine it with aquifer testing data, and associate a permeability with a specific number if we have enough testing data. So here's an example of a very old exploration log from the 1960s or 70s. And they don't normally, record information that's very helpful for a hydrogeologist, but in this case they did. And this is fracture data. And so what this means is the O stands for open fractures, the C is closed, and then the number is the number of fractures in this particular zone from, in this case, 3,513 foot depth down to 10 feet lower. So it's very highly fractured. And you can see that as you go down here, the closed fractures, there's 25% closed, and the closed would be ones that are sealed up with precipitation. But it's mostly open. So this tells me as a hydrogeologist, hey, this could be pretty good for water supply. Then geophysics, these districts are often, particularly at the early stages of exploration, there's a lot of geophysical lines that are run. This is showing induced polarization lines for a district. And there are many generations of IP lines in this case. And these can help to interpret and understand both the geology and hydrogeology. So here's an example. This is a IP line from 1969. And the geologists who worked with this at the time thought, okay, this has got to be a graben. It looks like a graben. So they assigned it that characteristic. So it would have a fault on both sides of it. One was clearly well known, the one on the right. The other one was speculated. So this was thought to be a fault. But I came along many years later, and I have the advantage of a lot more drilling information. So I had all this data, and I could tell from the drilling and the logs that actually what this is a contact between Cretaceous volcanics underneath tertiary volcanics. So the difference there is very important, and the difference in time between the Cretaceous and the tertiary in this case was about 30 million years. Well, that told me there was an awful long time there where you could get some erosion on that Cretaceous volcanic surface. And so what we're actually seeing is a valley that's been carved into the Cretaceous, and it's been filled with tertiary volcanics from the mid-tertiary. There's a fracture zone that I was looking for. I didn't see it in this. So fractures don't always show up. I know it's there because I see it in the wells, but it did not show up on the geophysics and in the water table. Another thing we do is look at these geophysical logs. We have a lot of logs. In this case, I noticed that this gamma ray log spiked up at some point, and I started to look at a lot of different logs, and I saw this exact same signature. So even though the volcanics are all the same, there's no difference across this, I know that something changed in the source of the magma. So it had a higher gamma count at this point than what's below it. Well, I could correlate this. This is like a bed in a sandstone. You can actually correlate this. And so I was able to see what the bedding dips were of these volcanic units based on this geophysics. And then, of course, geologic mapping. I mean, all of us love Google Earth, and we go out and we look at Google Earth and decide what we think is going on, but there's no substitute for going out in the field and looking at the rock. You obviously can't see the level of detail shown in these pictures from Google Earth, and this is very, very telling. So I'm going to spend a minute here talking about this particular rock type because it is a dream rock type for a hydrogeologist. This is an aphanitic rhyolite. You can see how fractured it is. And this is an actual lava flow of rhyolite. I'm not too far from the caldera where this was produced. So I have some pretty good idea of what this is. And the aphanitic part, and apheric is the other term, means that there's not much in the way of phenocrysts that are in this rock. It's very, very fine grained. That tells me that this volcanic lava flow was pretty hot when it came out. It hadn't cooled enough to allow precipitation of feldspar or quartz crystals. And so being very hot like that mattered because when it hits the ground, it starts to cool rapidly. And when something as with such a high viscosity as rhyolite cools rapidly, it cracks. It cracks like glass. And so, and here's an example of a surface. You can see horizontal slicken sides on this surface. That probably formed when this rock was still hot and moving, and tells me that, okay, this is a endemic secondary porosity for this particular formation, formed right from the beginning. So every part of this flow looks like this. And as you walk around, it's just remarkable how much fracturing and broken rock you have. So these aphanitic and apheric rhyolites are very good aquifers in volcanic settings. There's not many rocks in a volcanic setting that are a good aquifer. This is one of them in the right circumstances. So it's a siliceous magma with high viscosity. It came out at a high temperature, as indicated by the lack of phenocrysts. It cooled rapidly, which caused pervasive cooling cracks. The cracks are excellent secondary porosity, which extends throughout the deposit. The siliceous composition is nice because it's like storing water in a glass. You know, it doesn't react to the water doesn't react with the matrix, so it preserves its good quality for a very long time. But the one negative is you have to have a fault of some sort to interconnect these pervasive fractures with a production well. So we mapped this, and in combination with mapping large-scale structures as well. And we were able to build a well field that has provided tremendous amount of good quality water for a mine. Moving on to another topic, this is passive containment capture is something that open pits can create, especially in the Southwest US. So as the pit is deepened below the water table, and you stop mining, a pit lake will form. And in the Southwest, where the evaporation is very high, it essentially acts like an evaporative pump, which maintains that lake level below the regional water table surface. That depression in the water table creates a capture zone, which will persist in perpetuity. And it's called a passive containment capture zone, or PCCZ. And it can benefit the mine because you can use less engineered liner systems for leach pads, ponds, or other facilities that may discharge to groundwater. So it helps in the permitting of mine facilities. Over time, though, the pit lake will evapoconcentrate various things which could become toxic. So some analysis of that is also required. So here's a pit lake in Arizona. And this one actually has quite a low water level compared to the regional water table. And let me just talk about hydraulic capture and how it works. So this is a well situation where I'm pumping a well. I have some observation wells adjacent to it. I can tell that the two closest observation wells have water levels indicating that it's flowing towards the pumping well. And then another well that's farther out that indicates it's flowing away from the outermost of the two monitor wells. So I know that the hydraulic capture zone is somewhere between these two wells, like where the yellow line is here. And in a well pumping like this, the bottom of a hydraulic capture zone can be hundreds to thousands of feet deep. Now, if you go to an open pit setting, let's dig our pit. And the water table, of course, is depressed around it because they have to dewater it while they're mining. And then I put in some wells and I do exactly the same thing. I can see which way groundwater is flowing. Then I can determine that there's a hydraulic capture zone around this pit. But in a pit setting, it can extend thousands to tens of thousands of feet deep. It's a very, very large effect, partly because you're in bedrock, so the storage in bedrock is quite low, and therefore the effect of hydraulic capture goes much deeper. Here's the pit lake forms after mining stops, and you have evaporative pump, which keeps that water table depressed and therefore creates this hydraulic capture. So this is a large mine with a lot of different lakes, and it's doing exactly what I was just describing. It's creating a passive containment capture system. We know from extensive monitoring all around this mine that groundwater is flowing in towards these pit lakes, creating a hydraulic capture zone. And you can see in this picture, there is in-pit leaching going on. That's what some of these facilities are leaching operations inside. They don't have to have any liner because they have passive containment capture, which makes it a whole lot cheaper for them to do in-pit leaching in a setting like this. Now, one thing I encountered, I was on a project where we needed to, the regulator wanted us to prove that there's upward gradient below the pit lake. So we put in 2 wells, that's H1 and H2 here. And what we wanted to show was that H2, the lower one, has a higher head than H1, so it's upward vertical gradient. Well, something we didn't consider was that we've got faults all throughout the area here connecting into the pit. So what happens is this monitor well is connecting into the pit lake. So when you do that, H1, which is not connected to the pit lake, is actually higher than H2. So there's an apparent downward gradient, but that's not actually what's going on, because really H2 is seeing the pit lake. So there is still an upward gradient along this fault into the pit lake. And so it took a little bit of explaining, but we finally were able to get the regulator to believe us. So to demonstrate a passive containment capture zone requires both extensive monitoring and modeling. The monitoring you can use to show what's going on at the time of mining, and gives you the empirical data you need to build the model. The model is what allows you to look into the future to decide, is this really passive? In other words, is it going to be in perpetuity? So that the regulators often require that. Here in Arizona, they recognize that as a feature of mines that we can use. So the steps to building a groundwater model, there's a lot of them. Assemble and compile a lot of data, construct the conceptual hydrogeologic model. I'll go into that a little bit. Select the appropriate domain boundaries and model platform, then construct and test the model. Run the steady state model to establish starting head conditions. Then we check the calibration of the steady state model against measured data that we have. And usually we start from some point in time in the past when there's enough data to allow calibration. And often this is in the early 80s, because that's when monitoring became very widespread. And then we run the transient state model and try to match changes in water level elevations over time. And then we'll check the calibration of the transient model, then run our scenarios for whatever the mine wants to show in the future, and then conduct sensitivity runs to see what is the most sensitive input parameter for that, then validate the model, and finally prepare a report. So here's this is the Leapfrog tool that we use for looking at conceptual models. This is off of their website. This is a location in London, I think, in England. And it just shows kind of how it's a very convenient tool. You can take logs, you can import them directly, and this plots it up, and you can assign surfaces to key features. So it's a great tool, and I encourage you to use it. So this is another conceptual model. This relates to that cross-section I showed earlier, and you can see the different features that we're wanting to represent in the groundwater model that's going to come out of this. This is a different site, but this shows, you've got basin fill, that's the yellow. You have volcanic rocks, you've got intrusive rocks, the purple, and then you've got fractured Paleozoic sedimentary rocks. So this is all pretty beat up and complex site. You got to simplify it. You have to be able to simplify this to be able to model it. The other thing is that often we'll have a lot of surface mapping. So we know what's going on at the surface in great detail, but you have to speculate about what's going on at depth. Sometimes, like in the area of an underground operation or where the ore body is, there's plenty of data. In other places, there's almost none. So it requires a little bit of intuition, experience, and understanding of the three-dimensional characteristics of the geologic units out there. Once you have all that, then this is where you assign permeabilities or hydraulic properties to different units and distribute them according to what you feel is the appropriate distribution. And again, this is a simplification. It's way more complicated than this, but this is all we need for the hydrogeologic model. This is a model where we're simulating a river, and I've done a cutout here looking at the wells. So surface water features are also very important and add some complexity to some of the models we build. All right, let's move on to operations. Those of you who don't know, that is a tank house. That's where we plate copper out of pregnant leach solution. So what's pertinent to hydrogeology with regard to mining operations is the siting, construction, and performance of water supply wells. Like I mentioned, you have to have a water supply. You have to monitor the impacts of the mine operations on local and regional groundwater levels. You have to monitor local and regional springs, rivers, and lakes. The groundwater quality monitoring is required to satisfy various permits and rules. Dewatering open pits and underground operations is also often required and requires a hydrogeologist to help figure that out. You have to identify sometimes, and I'll talk about this is fairly new, but geothermal reservoirs can be used to enhance leaching. And so the temperature of the water is also important. And then you can obtain additional subsurface information from condemnation holes. So the mine will expand over time, and let's say they want to put in a tailings facility. Well, they don't want to put the tailings facility on top of an ore body. So they always have to go in and drill out and make sure there isn't anything under the ore body to some reasonable depth. Well, that's an opportunity to collect more information for the hydrogeologist. So production well performance is really critical part of an operating mine. Bedrock wells are typically very inefficient. That is, there's greater drawdown in the well than in the surrounding aquifer. And I'll show you an example of that. Mine operators can have a difficult time managing pumping rates and duty cycles. And I'm going to provide an example of one that I've analyzed in a way that I think is helpful to the pump operator. So this is a busy diagram. Let me just explain what you're looking at here. So the purple line here is the top of the well screen. So the purple line is the bottom of the well screen. The blue zones here are zones where I've interpreted fractures that could produce water for this well. The red line here is where the pump is set. The red zone is where you don't want the water level to get, or it could cavitate and ruin the pump. And then I plotted the brown lines here are the pumping water levels from transducer data, and then the green is the pumping rate. So the pumping rate is on the right side, water level elevations on the left side. Okay, so what you can see here is that so the water levels when they're pumped down, they depending on how long they pump them will vary quite a bit. And then they rise up to a point where it more or less stabilizes. So it's this top of this line that's pretty interesting to me. So it's going up and down. And what I did was I took a look at the average pumping rate, like for this particular interval, where the water levels are going down. What's the average pumping rate? And then what's the average duty cycle? So a duty cycle is how long is the well pumped? So 80% would mean, in a day, the well is pumping 80% of the day, or a week or a month or whatever this time period is. So I looked at that and then looked at the next one. It's going up. So here it's 461 GPM and a duty cycle of 80. Here it's going up. It's 442 GPM, which is not that much different than the previous one, but the duty cycle is 20%. Okay, so how are we going to compare these? We got three things to compare: the pumping rate, the duty cycle, and the change in water level. So this is the way I did it. I took and plotted this up, or made a table of the pumping rates for each interval of time, the duty cycle, and the water level change. So the way to compare three things is to make them two. So I multiplied the average pumping rate by the duty cycle to come up with this product. Then I plotted over here that product against the change in water level. Then I fitted a linear regression to it, came up with this equation. This in this case has a R squared, a correlation coefficient of about 88%, so that's not too bad. Then I looked at where it was zero, right? And using this equation, calculated that number. That's the product of GPM and duty cycle. And then for this particular pump, I know that it ranges in pumping rate between 200 and 500 GPM. So I assigned four different numbers and then calculated from this equation what the duty cycle would be for each one of those. And then plot that up and assigned a power law curve to it. So this line becomes the line at which no change in water level is going to occur, depending on the pumping rate and duty cycle if it falls on this line. So anything that falls above this line, water levels are going to decline. Anything below this line, water levels are going to recover. It also tells me what the sustainable pumping rate of this particular well is, which is at a duty cycle of 176 gallons per minute. So that's what I did. And then I took and plotted, like for the year 2021 for this particular well, each month. So I looked at how it was changing over the time over the year. And every month's a little different. There's different needs going on. And this is a complex well field of a number of production wells. So it's not always clear cut. But you can see that most of the months are, the water levels are declining. So I pointed this out to them, gave them this graph and these tools to use, and then looked at it again for last year. And this is what we found was they took it to heart and they changed their operations such that almost all of their months are below the line, indicating it's rising, and the well has been recovering since then. This is an important well because it has very good water quality, and they need that water quality for one of their operations, in particular the acid plant where they generate sulfuric acid. Okay, so changing topics again, geothermal water. So the leaching of copper ore is a microbiological process. The temperature does matter. So if you can get the temperature a little higher, the microbes are a little happier and they do their job more efficiently. Up to a point. If it gets too high, of course, it kills them. So you don't want to do that. In Arizona, we're seeing more and more of the use of thermal blankets. So they cover the leach piles with blankets that keep the heat in, and it has the benefit, secondary benefit of reducing evaporation off of these piles. So it saves water. But they're also looking at, and they talk to us about trying to use geothermal groundwater. It's very common to have warm water or hot water in the Basin Range province in the Western US. And we're not talking about the kind of geothermal that you use for power generation. That's not that high. It's more like hot tub water, and that works really well. So this has brought to attention to us that we need to pay more attention to the temperature of groundwater as we're compiling our information about the groundwater systems. Okay, let's switch to closure. So a lot of ore deposits are actually formed as a result of supergene enrichment. That is where over time groundwater percolates, or water percolates down through the upper part of like a porphyry copper system, and iron is transported upward and creates a Gaussian, iron Gaussian, and then other metals like copper are transported down and enriched in a zone on top of the ore body. So this is the oxide or supergene enriched sulfide deposits that you see at some of these big copper mines. So this process is also a problem in that it occurs when you mine something and you expose it at the surface. You're creating a discharge, a potential discharge that is toxic, and that's called acid rock drainage. And it's basically the process where sulfide minerals, mostly pyrite, are oxidized in the weathering environment to form sulfuric acid. With sulfuric acid, low pH, the mobility of metals is increased. So here's the equation that describes that process. So pyrite, here in the equation, combines with oxygen and water and eventually creates acid. So it depends how rapidly this happens, depends on the surface area exposed, the pH and oxygen concentration in the water and gas phase, ferric iron concentration, temperature and chemical activation energy and bacteriological activity. So here's a phase diagram. Everybody cringes when they see these, but they are useful. This is a ferrous iron sulfide solid. And at the ferrous iron ionic version is at a higher oxidation and lower pH zone. So what happens here is, as you begin to oxidize pyrite, you're moving in this direction from the solid phase into the ionic phase with increasing oxidation potential. This is the redox potential over here. And then the pH lowers to the left on the horizontal axis. So that's the mechanism that's creating the acid and the problems. The mobility, this table shows kind of the mobility of different things. You can see that in the acid column, there's a lot more highs for high mobility of these different elements than there is for the alkaline version. One counter to that is uranium, which actually has a very high mobility in alkaline environment as compared to the acid environment. But for the most part, it's higher with lower pH. And then different sulfide minerals have will also oxidize. And this table or this chart just shows the increasing resistance to oxidation as you go from pyrrhotite to molybdenite. But all these elements, all of these minerals will create acid rock drainage. So this is an example of a small discharge from an underground mine I worked at. This is like 2 gallons a minute. And you see it's very brown, it's very low pH, probably about pH 2. And it costs this mine several $1 million to deal with this little 2 GPM discharge. But I want to talk about a bigger one. This will be the last part of this talk. So the Gold King mine is in San Juan Mountains of Colorado. It was an absolute disaster, and so I want to go through some of the history here a little bit in some detail. The Gold King mine was discovered in 1887, and for most of its history, the workings were dry because there was a regional drain called the American Tunnel that was connected to another mine called the Sunnyside mine. Sunnyside mine closed in 1991, and then they closed the American Tunnel in 1996. Well, you can imagine what would happen if you plug up the drain for a district. Water levels are going to rise. And that's exactly what happened. They started to notice discharge from the Gold King mine adit number 7 in 2002. There was another nearby mine called the Mogul mine that was sealed in 2003. And then the flows increased at adit number 7 to greater than 300 gallons per minute, which was discharging into Cement Creek, which discharges into the Animas River. The Animas River discharges into the San Juan River, which discharges into Lake Powell. So this was not good. 2009, the Colorado Division of Reclamation, Mining and Safety, or DRMS, closed all 4 Gold King adits by filling entrances with old mine backfill. They included drains that were installed to prevent the buildup of pressure. But there was a partial collapse of this. In 2014, DRMS asked EPA to reopen and stabilize the number 7 adit. The seepage was observed to occur 6 feet above the floor of tunnel. It was assumed that that meant there was 6 feet of water behind the earthen dam. EPA began work and hired a contractor in June 2015. When they began work, they noted that a landslide had covered the drains. They planned to excavate down to level observed seepage, top of the water pool, and then insert another drain into the pool. At 10:51 a.m. on August 5th, 2015, a backhoe operator saw a spurt of water from a fracture adjacent to the plug, indicating high pressure water behind the plug. That caused the release of 3 million gallons of acid mine drainage into Cement Creek. So here's the setting. So Gold King is up here in the middle of San Juan. This is Silverton. And then the Animas River runs down towards Durango. Durango's down here. I'm going to see if I can get this to, I'm going to have to stop sharing here for a second and get this started. Okay, I hope you can see that. This is the number 7 adit. And I'm going to show what the EPA released this video showing the results of, wait a minute, are you guys seeing this? This is shared, right? Kathy,
Yes, Doug, we're seeing it. Yes, we
okay,
are.
all right. It's hard for me to tell. Anyway, so this is the actual from the contractors as they were doing this. It's pretty remarkable. So they just started noticing this leak.
We're getting really high. You gonna go close it up?
Too late for that.
What are we doing now? Get a little video of this next time.
So they bleep out a lot of stuff here. I'll just move this along a little bit. So that's 3 million gallons of acid mine drainage going down Cement Creek. I'm going to stop this and go back to the slideshow. Hold on one second, please. All right.
Perfect.
There we go. So this is what it looked like down in Durango after all that 3 million gallons of acid mine drainage made its way down there. I actually came out a week later and I stood on this very rock and it was mostly gone by then. So it was very transient. It didn't stick around for too long. But obviously visually it's horrible. And of course, all the downstream users, including a number of the tribes, were really upset about this, not to mention Durango. And there's a lot of concern about drinking water and things like that. So they've been doing, and APA has been doing work ever since then, trying to put together a good long-term remediation plan and system for this. And these aren't current, so I'm not even exactly sure what they're currently doing, but I know that they have built a lot of facilities up there to deal with this water. So there's a lot of lessons learned here. Obviously, some really bad decisions were made along the way that should have been thought through more carefully. They shouldn't have just sealed up the tunnels without considering what was going to happen when the water level rose. And that's something that I've done in the past, is gone into underground operations and carefully mapped all the workings to figure out the interconnections, where water would rise to and discharge from after it's been bulkheaded. And so anyway, this is in a unique situation that hopefully isn't going to get repeated. I'd also just like to point out that we're going to have our 2024 annual national meeting in Durango, and I'm hoping that we can get up and take a look at what's going on up here, because it's a pretty area to be in, and it's unique. There's a lot of mines. So conclusions. Groundwater is both a curse and a blessing to mining projects. It's a curse if you have too much or too little. It's a blessing if you have too much or too little. So it just depends on the situation. And in the planning of a mine, you can take advantage of a lot of information that's being collected for other purposes that helps in the hydrogeologic evaluation. A good conceptual hydrogeologic model is essential and should be based on sufficient field data to justify the components of the model. Groundwater supply for a mining operation should be identified early in the planning process, because it just takes a long time to develop a water supply. It's not an easy thing to do often. And there's a lot of legal access issues that are very time consuming to deal with. So it's not just about the hydrogeology or constructing the wells. So there's a whole lot of other things that go into it. And then always remember that mine plans change constantly. So you have to constantly go back and reassess the groundwater conditions. If there's a groundwater model, you have to recalibrate it periodically, and then revise your water supply needs or sources of water over time as a mine expands or contracts. So that's all I had for today. Hopefully you got something out of it, and hopefully I'll see you in Durango in 2024. So Aaron, we can open it up for questions. Or
Perfect. Perfect. Thanks, Doug. I really appreciate that. I know, Doug, you do have a hard stop here in about 8 minutes. So I'm going to start you off with one question, then we'll open it to the floor. When you work on your hydrologic models, what factors govern the sort of resolution of your model? You know, how fine resolution can you get? What are the governing factors for those types of models?
Yeah, in fact, I'm dealing with that today. We have a model that we need to build for an underground operation. And the question is, you know, we have to simplify it. There's no way we can simulate all the detail that's going to go into this operation. No way. So it becomes a judgment call, partly based on, you know, the computer resources required to run it. You know, if you have too many cells in a model, it takes a lot more CPU time. And, you know, if one model run takes a week to complete, you're going to have a very difficult time getting an adequate calibration, because it just takes too long, and time is money also. So it gets more expensive. So that's part of the way that we decide how much detail do we need is how hard is it going to be to simulate this? And then of course, there's also the issue of how much data do we have to support the model. So it's a judgment call.
One of the things I see in the chat from Robert North, he says that a missing element in exploration is often the accurate identification of the water level in exploration drill holes. Do you have any examples or suggestions for how you might measure and then subsequently model from drill hole data?
Yeah, I mean, one thing we've been doing more and more recently in recent years is going to the exploration guys where they're putting in core holes and then following up with vibrating wire piezometers in them, usually with 3 or 4 different monitor probes set at different depths, so we can get an idea of the water level, but also the vertical gradient, which can be helpful. So, and then you can also create a standpipe piezometer fairly easily and take some water level measurements from that. But in general, when they're drilling, it's very hard to figure out what the water level is unless you're using some kind of air rotary method where you can stop and let it recover. But only then can you trust it if it recovers quickly. So that's the limitation with that.
Okay. Also from Isaiah Hageman, he asks, how does GIS factor into the 3D modeling of the subsurface and hydrologic conditions?
All of our input files that we generate for models come from ArcGIS. So it's a really good way to assemble data in a way that's georeferenced, that we can then populate into a model, particularly these large complex models. It's just too laborious to try to do it by hand. So we try to always use georeferenced files of some sort. ArcGIS is the most common we use. And you can also do that from Leapfrog and then import directly into the model. So ArcGIS is absolutely a key tool for us.
Excellent. If you have other questions, you can unmute yourself and shout them out, or you can drop them into, one just popped into the chat. This one from David Adelman. When you draw potentiometric maps, how do you deal with understanding the water level over a very large array of adits that are near the active dewatering level, especially if you don't have measured data? Can you assume a constant level as hydraulic conductivity is high?
So the effect of underground workings, especially interconnected underground workings, is that it distributes hydraulic pressure. So if you go into a district with a lot of underground workings, the water table's usually flat, pretty flat, because the workings distribute the hydraulic pressure. I don't know if that helps, but that's kind of what I've noticed for mining districts that I've been in. But if it's a small operation with a small amount of workings, then all bets are off, and it does become complicated and confusing to figure that out. So yeah, that's about all I can offer for that.
From Doug Peters, he says that an issue on the exploration side often is getting the exploration staff to recognize that getting water info is important. How do you approach that, Doug? How do you communicate that to staff, that the water is a crucial piece?
I'll tell you what, now it comes right from the top, because everybody recognizes that, at least where I work, if you don't have water, you don't have a mine. So they're more and more tuned into the importance of water and the effect of mining on both the environment around the mine. The legal aspects are huge. There's huge lawsuits and things going on around water. So it's not hard for me to convey to the staff the importance of this, because they're getting it from their bosses, frankly.
Okay, and I think one final question here. This is from Perry Evans. He asks, do you have any references or publications for the duty cycle method to determine a sustainable pumping rate?
No, that you've seen everything I've done with regard to this, that was came out of my head, and I didn't pull it out of anybody else's paper. It was just something I dreamed up. So apologize, but maybe someday I'll publish something. I don't know. And maybe there's other ways to do it too that I'm just not aware of, but yeah.
Okay, I did see one more question come in. I will give that to you, and then I think we'll finish up. Edwin asks, do you use EPT, equivalent porous media, for your model, or do you use discrete fracture?
So it depends. For mines where the fracturing is a key part of the mining operation, for instance, an in situ copper leach operation would require us to look at discrete fractures. But for the most part, under most circumstances, we don't need to worry about that. Equivalent porous media is perfectly fine. And the data usually only support that assumption, because we don't usually have detailed individual fracture kind of permeabilities. But we have done both, but it's more common to just use equivalent porous media.
Outstanding. Well, thank you, Doug. I appreciate your time. It was a fantastic talk. A few questions that we've had. The slides will be available on the AIPG members page. So if you're an AIPG member, you'll be able to get in and get a copy of this presentation. It will be probably as a PDF file, Doug, am I correct?
Sure. Yep.
Yeah.
Yeah,
So
won't have the animations, so that's yeah.
Okay, we'll put that on the member page. And just a quick shout out, the last day of April, the last Tuesday of April, which I think is Tuesday, April 25th, we'll have Vitor Correa from the International Raw Materials Observatory. Vitor will give a webinar on that will focus on sort of global competition and positioning for raw materials. So we're going to be looking now at a really large scale. I really appreciate everyone's attendance. Please feel free to reach out to me if any of you are interested in giving a webinar that would focus on economic geology or water issues. I really appreciate it.